Welcome everyone to the 924th meeting of the Amateur Telescope Makers of Boston. It's October. I love October. Halloween. It's always scary stuff going on. Any October birthdays here? Raise your hands, please. We have one birthday in October. Jim, happy birthday. That's like rare. All right, wow. Again, really want to welcome. We've got a really action-packed meeting. I'm really excited to have Peter here. He's going to give us a talk about our safe haven here on Earth, and maybe not how safe it is. So we'll see. I'm looking forward to that. The Patriots game is on. If anybody really wants to know, I can flash up the score every once in a while. Okay.
Just no date.
And with that, why don't we get started? Observing report. Okay. All right, please.
All right, this is for the pin, and $5 is your pay for the year, so you're now officially have a salary. All right, as always, I try to put up a little, some type of saying. No known roof is as beautiful as the skies above. I like that. Is anybody familiar with Michael O'Muirtarg? I guess is how you pronounce it. Irishman. Anybody know who he is? No. I didn't think so, and neither did I, so I Googled him. And he's a Gaelic sports announcer. And I guess he's the Vin Scully of Gaelic sports. But I was kind of interested. I got some other of his sayings or phrases, and this is as a sportscaster. So here's one of them, for instance. He's talking about, I guess it's a soccer game, and he says, Anthony Litch, Cork cornerback, will be the last person to let you down. His people are undertakers. Ouch. And then Teddy McCarthy to Mick McCarthy, no relation. Nick McCarthy back to Teddy McCarthy, still no relation. So he must be a very interesting guy to listen to. Next slide. Well, a couple things going on the 13th, Sunday, from 6:53 to 7:27, there'll be a double shadow transit of Jupiter. It's the last one this year. And you might want to scout the area out, because I know from my backyard I can't see Jupiter at all, so I'm going to have to go. I'll probably try the Clubhouse itself. Somewhere we get a nice view of the southwest sky where we can pick up Jupiter that time. It'll be involving Europa and Europa and Io, and Europa will begin the eclipse and Io will finish it. But there'll be about a 30-minute stretch shown up there where the two shadows will be visible on the planets. On the 28th, Uranus is at opposition. It's in the southwest corner of Aries right now. Kind of a barren field, but if you get a chart like from Sky and Telescope or Astronomy, you'll find out exactly where to look for it. It'll be magnitude 5-7 and visible in binoculars. Daylight saving time ends on November 3rd, so we get that extra hour now of darkness, which is something we all look forward to. And on Monday, November 11th, from 7:36 in the morning to 1:04 in the afternoon, there'll be a transit of Mercury. That's a big event. We haven't set up anything in the Clubhouse, but I'm sure some of us will be there. I'd certainly like to view from the Clubhouse myself. Now here's the thing. The next one won't be visible until May 7th, 2049. So except for Corey and Kira, none of us will be alive at that time. So you guys enjoy it. Is anybody else here that's at a safe age with him? I'll be 102, so I'm not planning on it. I think that, yes.
I showed my wife, who was not really interested in this stuff, a transit of Mercury for a solar filter.
Oh,
and she looked at it, and this was before the eclipse in Missouri that we went to. She said, I hope the eclipse is going to be more exciting. It is kind of unimpressive. Venus is a lot better.
You know, it's a rarity. I think some things are interesting because they're rare. I mean, you look at a supernova in a galaxy, it's not particularly exciting, but you look at something, that star blew up 30 million years ago, and it's kind of fascinating knowing what you're looking at. But you're right. But it's the last one that we'll get a chance to see. So, somebody had their hand up?
Yeah, it's
yes.
also, it's Veterans Day.
So a lot of places.
So a lot of places will be closed.
So come on out.
Yeah.
Okay, there will be two, by the way, before, but they're on the other side of the world, so 1949 is the next one. So if it's cloudy, you guys are okay, the rest of us will be screaming. What's that?
You mean 2020.
What did I say?
1949.
I was already 2 years old. My brain is still back in 1950. Next. The sky object of the month, the challenge, is NGC 7448 in Pegasus. And is Doug Paul here? I know Doug sent me a picture. I just got the email today, so I haven't had a chance to look at it. And let's see, I've already forgotten where exactly it was. I think it was near, Marcab. It's over here. That's Marcab down there. And this chart, by the way, if you go to the AAVSO website, they have a variable star plot. And normally the way it works is you put in the name of the variable star, like SS Cygni. You pick a scale. There's ways you can play around with it. And you can print out a chart. But you can also put the right ascension and declination. And it'll print out a chart with an X marks the spot, which is how I got this chart right here. It's right in this area right here. Very accurate plot. And you also have the magnitude of the nearby stars, which is kind of next to help. But I found this is a great way to print out charts. And with that, you can go from an A scale, which I think is, I'm going to say 5 degrees, down to even F and G scales, where it's a fraction of a degree, and you go down to 17th, 18th magnitude. And you can pick and choose, which is really nice to make these charts. So I've been using that lately. Next, we have Mario and Doug's pictures of it. And our catalog, this is one of these peculiar galaxies. It's got a central nucleus, but then it has little patches. Spiral arms are kind of separated. That kind of got his interest. This is Mars, which is 32-inch. And Doug Paul isn't here, but I forget, it's a much smaller telescope, obviously, but he's been giving us some nice images as well. And next, just a sketch I made. And we might go back and forth on this. Not too much. That was with a 10-inch telescope. And I got to tell you, one thing you want to do is let your eyes dark at depth. It took me a long time before I was able to pick it up. I located the area by star hopping, and I started with low power. But when I get to the area, there's no way I could see anything. So then I jacked the power up. And this is about, I think, 140 power I used, and about maybe 0.6 of a degree across. And I'll just point out these 3 stars right here. That triangle, if we flip back, those are the 3 right here. There's a galaxy and a star over there. Now we'll go back forward. And I honestly wasn't sure that I'd seen the galaxy. I knew the general area, but I made a sketch. I did see it a little bit elongated, but I tell you, it took a long time. So if you have a small aperture telescope, you might not have too much luck with this unless you went out in a very dark sky location. I think you could pick this up with a 6-inch telescope from, say, the desert someplace. I was in an area that's about magnitude 5 was the limiting magnitude, and I had a lot of dark adaptation before I picked it up. And that's about it. Any questions, comments? All right, keep looking up.
Okay, so Dr. Peter Vereš, did I get that right?
Yes.
Somewhat right. He's going to speak of the current state of planetary defense, the past, present, future of asteroid and comet discovery, Earth impacts, and what we can do about potential impactors. So Dr. Vereš obtained his PhD at Comenius University in Bratislava, Slovakia. After a year as a research faculty at the university, 3 years as a postdoctoral researcher at the University of Hawaii, and 2 years as a Caltech Postdoctoral Scholar at the Jet Propulsion Laboratory, he joined the Harvard-Smithsonian Minor Planet Center and as a staff scientist in 2017. He's worked as a member of Pan-STARRS telescope team in Hawaii and co-discovered thousands of asteroids and dozens of comets. His research is related to meteors, discovery of asteroids and comets, simulation of survey telescopes searching the near-Earth asteroids and potential Earth impactors, and physical characterization of asteroids. He works on operations and development at the MP Minor Planet Center, software pipeline. So thank you very much for offering to speak with us today, and we're really looking forward to it. So thank you.
Thank you very much, Tom, for inviting me here, being here with you tonight. And I'm going to talk about planetary defense, which is about asteroids and comets and the Earth. It's not about another defense. So let me start. So I will start with this picture, with you may be very familiar with. It's an impact crater that is located in Arizona, maybe 30-40 minutes from Flagstaff. It's in Arizona Plateau, high altitude. And in the past, people really didn't know that this thing was caused by a giant meteorite. They didn't know that, and actually the story is quite interesting. So approximately 100 years ago, it was the chief geologist of the United States Geology Survey, Gilbert, who kind of started thinking about what if this phenomenon was caused by a cosmic body? Because in the area of this crater, which is like 1 kilometer wide and 170 meters deep, they found many fragments of iron-nickel meteorites. And those were kind of weird because the fragments were not like pure meteorite, but kind of melted with the local soil, the local rocks. They were scattered around. So the question was like, what is this all about? But the main problem was that at that time, people thought that all craters on the surface of the Earth or even on the Moon were caused by volcanoes. That's what people saw on the Earth, like, oh, why this is not a volcanic crater? That was a question. So he kind of was a scientist, so he thought about, okay, so if this was caused by a giant body that hits the surface, then when the hole was created, the same amount of the mass that was in the hole before should be kind of in the vicinity surrounding of the crater. So he kind of went around and kind of summed up the volume of the matter that was scattered around. And he was expecting to find the same amount of matter scattered around, but surprisingly, it wasn't enough. It was just almost nothing was around, just a giant hole and nothing around the hole itself. And so his second argument was, okay, so if there is a giant iron-nickel meteorite that hits the surface, it should be still buried under the surface. And it should be of the size of the crater itself, basically. That was what people thought that time. So he expected if this is made of iron and nickel, it's magnetic. So he went around with his magnets. He was expecting to see that basically he will find some magnetic anomalies. He didn't find anything. So his conclusion was this crater was actually caused by just as a volcano, but not with the lava, but just with the steam explosion. And the occurrence of the meteorite fragments around is just a coincidence. A little bit later, another person came to this story. It's Daniel Barringer, who was by study actually a lawyer. He studied at Princeton and University of Pennsylvania, but he went into mining. So he started his mining company, and he surprisingly kind of got into this story. So these pictures are showing you the typical craters that you find on the surface of the Earth, and these are volcanic craters. So you may notice that these craters are having different shapes. So they are not really circular, they can have totally random shapes, are missing parts of the slopes. So because they originated by a different way as a volcanic crater, as a craters created by asteroids, but people didn't know that time. If you look at the Moon, you see many craters on its surface. But if you really look closely, you will figure out that most of the craters are actually of a circular shape. Only a very small fraction of the crater is not circular on the Moon. I'm not talking about craters that are circular, but probably missing the part of it because there was a second impact, but they are kind of circular in most of the cases. That's the main difference when you spot if you compare a typical volcanic crater and an impact crater. So another zoom on the surface of the Moon, most of the craters are kind of circular impressions. So Barringer's story is all about that. He kind of started thinking like, what is this is really about a cosmic body that hit the surface. He also tried to approach this by a scientific way. So basically, he kind of figured out that there is a lot of mass around the crater that is kind of molten. So basically, he was thinking, there must be a lot of pressure and temperature around to cause all this destruction that was around. He could not imagine just the steam explosion would cause all this. And then he also found quite interesting that he didn't find like individual meteorites on the surface. It was kind of molten with the rocks. So it was like, this is impressive. It's kind of some kind of heat and shock wave or something really caused this trouble. But he was still expecting that the meteorite, the iron meteorite, and most of it is still under the surface of the bottom of the crater at that time. he also figured out that the crater rim around the crater is kind of upside down the layers. So it seems like something hit it and kind of overturned the rim upside down. So it doesn't seem like a typical explosion of a volcano, not at all. He also didn't find any volcanic rocks around, so it doesn't seem like a real volcano. So he kind of experimented with the shape of the craters. He started shooting bullets into the ground. He figured out all these little tiny craters that he created are circular. So he's like, so the meteorites are hitting at the high velocity, so maybe this is how it all started. So he kind of figured out that, okay, so if there was a giant meteorite that hit the surface of the Earth, that would be really large. So we calculated it should be like millions of tons, and when it's still below the surface, it will bring him a lot of profit. Because he was a businessman, he was into mining, so his primary motivation was not really the science part, but to make money out of that. So he even computed like a profit of $250 million if he would find the meteorite that is almost of the size of the crater beneath or below the surface. So he started in mining operations. He actually built mining shafts on the bottom of the crater. Surprisingly, he didn't find anything, no meteorite. So he definitely found that the bottom of the crater was heavily compressed. So the rocks were behaving differently there. So unfortunately, he got into groundwater, so his shafts were kind of flooded. So he was kind of starting losing the money, and his investments were not very going well at that point. So at some point, the company got kind of upset, and he then was thinking maybe the impact was not from straight top, but it was under angle. So he thought maybe the iron meteorite is kind of on the side of the crater, because it seems like the rim is a little bit larger on one side than another. So he started to drill even on the side of the crater, but he didn't find anything. So the company, the mining company, kind of hired astronomer Moulton and asked him, please do some calculations for us and compute if you have an impact of an asteroid of a given size, what happens to the body. And Moulton actually computed the impact velocity and computed the energy that was created. So he concluded the energy is so huge that basically most of the impactor, the asteroid, just evaporates instantly at the moment of impact. So that kind of decreased the estimated mass of the remaining body to only 300,000 tons, which was like from 10 million tons previously. That's not much of a profit from Barringer. And that wasn't enough, so Moulton was really eager, and a year later, in 1929, he published 127 pages worth of paper, where it did in details describe what's happening when the collision appears. He basically derived that basically almost all the impacting asteroid just evaporates at the contact, and a few days later, Barringer got a heart attack and he died. And he basically lost all of his fortune. But fortunately, the crater itself still belongs to his family, so you can visit it and learn something about it. So this is some kind of a start of the planetary defense and how we understood that planetary bodies hit each other, and even the Earth is not protected from there. And in the 50s and 60s, more science was added into it. It was a study of geology and the rocks that were found around the crater, called shatter cones, how the pressure and temperature actually change the shape and the structure of the rocks that are in the vicinity in the crater. And it was Shoemaker in 1963. He kind of figured out that the impact craters look very similar to craters that were caused after nuclear test explosions that the United States conducted in Nevada. So look at that. It's circular, and the shape really looks like an impact crater. We kind of figure out it's totally different if you shoot a bullet into the ground, which is much slower than the impactor, or if you just throw a rock into the mud. But it looks different because it's basically explosion. That's what happens when an asteroid hits the surface of a cosmic body. It's an explosion. It's a spherical explosion, then just creates the hole, and most of it just energy and evaporates away. So, a few pictures I took when I was there. It's a nice place to visit. So currently there are about 180 impact craters identified on the surface of the Earth. I have to say it's not easy to spot them, and most of them are only discovered recently. The problem with Earth is it has atmosphere, it has water, it has continents that drift, it has not just the weather, but also the continental plates, how they move in geological ages. So most of these craters are hidden basically below the surface. You cannot really see them easily. And many times you just study magnetic anomalies, you have to go to the place and really drill to find the compressed rocks, etc., etc. So these are the locations only of the craters that have been found so far. So this is the same plot, but showing the scale and the size of the craters. Kind of some are smaller, some are larger, and have different ages. Well, it's not always about the very large asteroids that hit the surface. You might be familiar with this one. It happened in Russia in 2013. It's the Chelyabinsk event, and it actually caused some trouble. So the body itself didn't even hit the surface at the cosmic velocity. Only a small fraction of it survived. But the shock wave that that was created during its explosion in the atmosphere, like 30-40 kilometers above the surface, caused a lot of damage on the surface. Usually it was the windows that were basically broken, and people who were standing and looking through the window, like looking, wow, look at that, were injured with the shattered glass. And as you could see earlier in the video, it was a pretty strong shock wave. And after that, we kind of understood it's sometimes not only about the giant meteorites or asteroids that hit the surface. Even the smaller ones like this one can cause injuries and damage on the surface. And this body in size is not very large. It was only like about 20 meters across. So this is another example that didn't happen about the surface of the Earth near the city. Nobody saw it. This was in the Bering Sea in 2018. But it was captured by the meteorological satellites that are capturing the atmosphere. So the little thing that you see over here, it's basically an impact of a small body that evaporated, and the thing that you see is just a smoke cloud that is disappearing in the frames. So thanks to the satellites we have observing the atmosphere of the Earth from above, we have kind of information about things that happen far away from any cities or civilization about the ocean. So this is just a comparison how large were the bodies that I was mentioning. So the human is the little thing that looks like an ant on the top, right? The Chelyabinsk asteroid from Russia from 2013 was about this size. That's the Kamchatka bolide that was shot over here. It was a little smaller. And 100 years ago, there was this interesting thing happening in Tunguska. Probably an object of the size of 40 to 50 meters exploded about Siberia as well. So again, these things did not hit the surface. They exploded in the atmosphere. So what is the key motivation in discovering asteroids and planetary defense? So, excuse me. It all started in 1998 when the United States Congress actually mandated NASA to discover 90% of near-Earth objects. That's the term I will use today quite often. It's an abbreviation for near-Earth asteroids or object. So the Congress mandated NASA to find 90% and more of 1 kilometer size and larger NEOs in the next 10 years. So it means before 2008. So what does it mean? What does it mean? Why 1 kilometer and larger? So if such a body hits the Earth, it will cause a catastrophe that is kind of almost on a global scale. So it's really almost a planetary killer. So it's kind of important to find it first. Such a thing exists. So that goal was actually fulfilled in 2008, and we believe, 95% of these near-Earth objects that are larger than 1 km in size. After that, there came another act that is called the George E. Brown Act, or so-called Near-Earth Object Survey Act, that mandated NASA to find 90% of objects larger than 140 meters in the next 10 years. So these objects, if they hit the Earth, they cause a local damage, but it's still significant if they hit the surface. So that was the next goal. But the truth is, now it's 2019, and the current state is 30%. So that goal was not met. So what is the main motivation about planetary defense or discovering asteroids and dealing with that? The number one motivation currently is the planetary defense, obviously. The number two is the science and research, because we would like to learn how the solar system was evolving, how the asteroids got into space close to the Earth, because most of them are really between the orbits of Mars and Jupiter, and then much further away beyond Neptune. And the third one is even more fantastic, but it's becoming more and more popular, asteroid mining and resources. So it may be possible, and some private companies are starting into looking into this, making some business in mining from near asteroids. So that's a different topic by itself, but I find it quite interesting. So, so how does it work nowadays, and where is planetary defense? So 3 years ago, at NASA, the new office was established. It's called the Planetary Defense Coordination Office. It has a nice logo. And this office was not based from out of nowhere. It was actually based on existing group of people who were managing the Near-Earth Object Observations program and funding telescopes around the world who are searching for near-Earth objects since like 20 years ago when all these programs started. And what are the main kind of four things what they do? Number one, find those objects. Number two, warn. Number three, mitigate the collision. And number four is coordinate people, not just in the United States, but around the world if such a thing is found, and just try to find them. So I can also mention the funding, so how this thing is getting more and more serious. 10 years ago, when I was about starting this business, the annual budget of this group was about $2 to $3 million to fund telescopes around the world. 3 years ago, the budget was $60 million. So the tell you it went from 2 to 60, and 2 years ago it went from 60 to $160 million. So that's the budget that NASA and US government is spending. So it's taking this topic very, very seriously, and I will tell you later what was really achieved in the last 10 years. So I have to start with these two groups that are funded by Planetary Defense Coordination Office directly. The number one is placed this year at the same building. It's called the Minor Planet Center. I work for them. This center has been here for basically 50 years. And it's the center that basically takes all the observations of asteroids and comets around the world from more than 2,000 observatories that we have on our list. And we take the observations, we compute the orbit, we identify if it belongs to a known asteroid, if it belongs to an unknown asteroid, we compute the orbits, and we serve as a service for the entire world. So our data are free, are public. So if you go to our website, you can search for a given asteroid and compute ephemeris. Where is it on the sky, what is the magnitude, and so on and so on. So that's our job of the Minor Planet Center. Number two, that's a center that's at JPL, where I worked for 2 years. That's a center that's kind of specialized in computing the impact probability of known asteroids, for instance. They're kind of serving the community as well, and its products are also available for free and have really nice online tools, not just about impactors, but you can even try mitigation of how to mitigate the impact of a given asteroid that you simulate. So what is the situation right now? So I have to mention that if you go to the smaller sizes of asteroids, you have more of them. So we kind of think that there are about 1,000 objects larger than 1 kilometer around near-Earth space. Just remember number 1,000. We basically found 950 out of them. So basically we are almost safe for the large ones. But if you go to the smaller ones, so this plot shows basically the number as a function of size. So this is the size of the asteroid. This is 1 kilometer. This is 100 meters. And the colors kind of show what happens if such an object is the surface of the Earth. What is the impact? It has a global impact, continental impact, regional impact. If the city can be destroyed or there is no serious impact. But this is the number of objects that are in the space on the log scale. So if you go to 1 kilometer size object, which is here, you find there are around 1,000 of them in the near-Earth space. If you go to like 100 meters, you will get to the number of 30 to 50,000. So you could go to millions if you go to 10 meter size of this object. So the number really goes up. But the percentage of them we found goes down. So we are about 30% at the NASA mandate. It was still not fulfilled, so there is still a lot of work to be done. But we are not sleeping. The work is really ongoing. So this plot kind of shows you how many near-Earth asteroids are discovered as a function of time. So we are in almost 2020, 2019, and there are more than 21,000 near-Earth asteroids discovered. The colors are just showing you which are in the 1 kilometer size range and larger, 140 meter size and larger, and all of them together. So you can kind of see that 1998 was when the Congress mandated the NASA. So before that, it was basically nothing. Very, very slow, nothing was going on. After 1998, several survey telescopes were started and funded with only one goal: find near-Earth objects. And then that funding really paid off. Look at that. It went up. And the second generation started, I would say, after 2010. That was the time when I started working for PanSTARRS, which is the survey telescope that started working in Hawaii. So the number kind of goes up rapidly. So the work is really going on. So as I mentioned, there are several telescopes around the world that are doing this job, and these telescopes are not the same. So at the beginning, like in the first 10 years of operations, it was mostly the Lincoln Lab telescope that is depicted in the blue color. So these are histogram by years, how many NEOs they discovered. And later it was different groups. The green one is the Catalina Sky Survey in Arizona, and the pink one is the PanSTARRS telescope in Hawaii. So if you go to the current times, let's say the last 5 years, you will see the vast majority of NEOs are discovered by the Catalina Sky Survey in Arizona and PanSTARRS in Hawaii. So these are the main contributors to today's discovery of NEOs. So what will happen if such an object hits the Earth? So I have to mention that it depends how often it hits the Earth as well. Because as I mentioned, if you go to the larger sizes, the less of those objects are in the vicinity, the impact frequency is kind of low. So that's good luck for us. So for instance, we are talking about object of the size of Tunguska that happened in Russia 100 years ago. That happens roughly once per 500, once per 1,000 years. So the frequency is kind of low. If you talk about impactor that kind of probably killed the dinosaurs 64 million years ago, that happens once per 10 million years. So the frequency kind of depends on how large is the asteroid that hits. So for the small ones, like what happened in Chelyabinsk, it's probably once per 10 years. So how many asteroids were found? So I personally like this animation that is showing all those 21,000 NEOs around the Earth, how they move. So Earth is shown here, as you can see in this part. This is Earth, this is Mars. So all those that are moving around are asteroids, and we are trying to track all of them. So how large are the asteroids? So they are much smaller than Earth, they are much smaller than Moon. Just comparing the size of the Earth and Moon to the largest one of those, and this asteroid that is now being upgraded to the status of a dwarf planet, Ceres, that is 1,000 kilometers across. But asteroids are much smaller, so the Vesta is the second largest in the main belt. And we go to the nearer asteroids that are usually even much smaller than the main belt asteroids, so that's the size. And these are some images of asteroids from the spacecrafts that visited them from close. So you could kind of see that they have really shapes that are not spherical, they are really having shapes of sometimes potatoes, irregular shapes with impact craters on the surface, kind of cracked. So they are kind of fragments of larger bodies that were probably created when the solar system was formed 4.5 billion years ago. And it's even more interesting if you go to the smaller sizes. So this is one of the smallest one ever visited by the spacecraft. This is Itokawa. It's the near asteroid observed close by Japanese spacecraft Hayabusa. And you see it's really different from the large one because it's not really a solid piece of rock, it's actually a pile of rubble. So it's kind of interesting. It just looks like there is a large number of loose rocks just on the surface of it. So this is how asteroids looks like from close. So let's get back to planetary defense. So what do we actually do in this era of planetary defense? As I mentioned at the top of this picture that I took from Lyndon Johnson, who is the planetary defense officer at NASA. So at the top, that's the Minor Planet Center that gets all the data and shares it to the world, to the public. But at first we need to search for them. So it means we have to discover them, then we have to track them. So the discovery itself is not enough. If you see an asteroid for the first time, it's just a dot on the sky. If you leave it that way, it will get lost. You need an orbit. If you have an orbit, you can predict where it is in next year, in 10 years, in 100 years from now. So it's discovery, it's follow-up to get the orbit right, and then we can characterize those. What does it mean? So we need to figure out like how large they are. Something about their physical properties, how quickly they rotate around the axis, etc., etc. And then we need to plan and coordinate, because often it's not just the thing of a single telescope, it's a collaboration. So one telescope discovers an asteroid, but other telescope needs to do the follow-up quickly. So it's kind of a collaboration around the world. And another part that is kind of important for planetary investment is the mitigation. So at this stage, we are not really ready in sending a spacecraft to save us if such an object is discovered, but we are getting there. So I can mention that. So on the top, next to the Planet Center, is the center at JPL. He kind of computes the impact probability of potential impactors, how dangerous these objects are. So what about the discovery? So as you may know, if you point your telescope to the sky, you have tracking that tracks with the stars. You will see your stars are not moving, so you can watch galaxies and opal clusters, globular clusters, etc., etc. But sometimes there is some dot that is going across your image. So in this case, I'm showing you asteroid. It's a 10,000-year asteroid that was discovered in the Pan-STARRS in 2013. And so asteroids are quite obvious in images if you take a time series of images. So asteroids are dots that are moving in front of stars. So all we do is basically compute the position of those asteroids with respect to the stars, and people send coordinates to Planet Center of these asteroids, and we compute whether they are known, if they match positions of known asteroids, or we just add them to our database as new objects. So where are the telescopes that are currently mostly contributing to discovery of NEOs? So as I mentioned already, number one is Pan-STARRS telescopes. It's two of them actually. So it's on the left, upper left corner. So there are two identical telescopes, 1.8 meter in size, very wide field. They are located at the top of Hayabusa in Hawaii. The second trio of telescope is in Arizona. So it's near Tucson. So these three telescopes on the bottom are contributing with Pan-STARRS most currently. Number three is Atlas telescope that is on Hayabusa and Mauna Loa. So those are two telescopes. They're kind of different from these guys on the bottoms on Pan-STARRS, which are large. Atlas is only 50 centimeters in size. So you would think quite a small telescope, but again, their strength is in the field of view that is very large. And we also have NEOVISE, which is a form of WISE telescope. It's an infrared telescope around the Earth that is observing in infrared and also searching for asteroids. So what is a survey telescope? As I mentioned, these telescopes are specialized in finding near asteroids. So that's a new type of a telescope, and its main goal is to provide very wide field of view, and it has to go as deep as possible in terms of limiting magnitude. So Pan-STARRS has the world's largest CCD camera. So this is the image with John Tonry, my ex-colleague from Hawaii. That's the camera he's holding in his hand. It's this wide. It's like 40 centimeters. And it consists of many, many chips. So it has like small CCD chips that are only 600 times 600 pixels, but they are put into arrays. So what you see on the top is actually the rough image from Pan-STARRS. It looks kind of ugly with all those gaps, doesn't it? But it does the job. So basically this field has 7 square degrees, and it can go down to 20-second magnitude in 40 seconds. So it's basically a scanner of the sky. So you would like to capture as much of the sky as possible in as short as time you get. And that's the future, obviously, not just for NEOs, but also other kind of astronomy that have surveys to basically scan the sky. So this is just comparison of the field of view with the composite of many, many CCD chips. So this is the field of view of Pan-STARRS. This is Andromeda galaxy in the sky. So this is 7 square degrees. LSST will start in 2 years from now. It's an 8 meter class survey telescope, and that's the field of view of LSST as will be. So this is ZTF, even much larger. So this is Zwicky Transient Factory on Palomar. It's even larger, but it's operating right now, but this has lower limiting magnitude. This goes to plus 20th magnitude. This is 22nd, and this will go to 25th magnitude. So that's the future of astronomy, not just the surveys. And just for information, this is one of the, I would say, sweetest toys in the current market of astronomy. This is a 100 megapixel monolithic camera that Atlas is using.
It is really sweet.
So this is something that I'm not sure if this is on the market, on the shelf right now, but having such a large chip without any gaps, and this is a back illuminated high quantum efficiency chip. So you can imagine how beautiful are pictures from this camera.
John said the chip is pretty expensive.
Oh yes, yes, yes.
Then of course you have to build the doer, but I think he give you the designs for the doer.
So I saw images of this.
But having a telescope with that big, a flat field, is also one of the challenges. Atlas itself is designed to give you a very flat field that matches that size detector. And it's literally like this big. If you can imagine a chip that big. I have some pictures of John holding that in his hands to get better scale.
So that was another challenge at Atlas itself. You may think, oh, it's just a telescope of a size that some amateurs have, like 50 centimeters. It's not that, right? Because it has to be wide field and really corrected for the flatness of the focal plane. So it was quite complicated to find a vendor to make a telescope for Atlas.
And
so that's another
the
part.
The corrector plates were originally defective, and so John had to let another contract to a different company to get them made. Now he's getting wonderful images.
That's true. We could see that the limiting magnitude also shifted. It was like 19, now it's about 28 magnitude, so they improved a lot in the last 2 or 3 years. So what about characterization of asteroids? So there are assets that are directly paid by NASA. So they are using 2 radio telescopes actually in Doppler mode, so they can really observe objects that are close to the Earth and find out not just their distance with the Doppler radar, but kind of figure out what is the shape of those objects. And infrared telescope, one is on Mauna Kea, that's IRTF, and one is still in space, Spitzer, that has been used for characterization of already known and discovered asteroids to figure out what are their shapes and thermal properties. So these are some nice radar images from Doppler, and thanks to the funding of NASA, we are getting more and more images of those. So if you visit JPL website and is curating this program, you will find nice animations from Doppler radar, and sometimes you see not just the shape, but you discover the moons. So that little white thing that is kind of flying from bottom to the top, that is a moon of an asteroid that was discovered. So as you could see, you can really discover really weird shapes, and sometimes you find that asteroid is not a single, it's kind of a binary asteroid. So those are 2 asteroids rotating each other, just discovered by the radar. I'm not sure if this was the Goldstone, it's the Deep Space Network system, or this was Arecibo, Puerto Rico. So you can also do a lot from your backyard. If you have a telescope that is relatively small, you can do light curves. So what is light curve? You can just point your telescope at an asteroid that looks like a dot, and in a very short time interval, you just notice amount of light that is reflected from the surface of the asteroid. Because asteroids are not spherical, they have weird shapes. Depends on what part of the phase are showing to you, the light curve kind of changes as a function of time. So the typical light curve period is about a few hours. And from those things you see on the left, just kind of light curves that look sometimes like a sine wave, sometimes kind of a deformed sine wave. You can derive shapes. Even you cannot really see the asteroid from close, but you can still have some idea what kind of shape of an asteroid it is. You can really figure out that the asteroid is binary because you see the primary light curve and then you see something is going in front of it. So this is another way how to figure out the shapes of, I think currently almost 10,000 of asteroids are known about their shapes and rotations just from the light curves. Spectroscopy is another nice tool how to figure out what is asteroid made of. So basically asteroids are not shining with their own light, it's just a reflected light from the surface of the asteroids, the solar light. You just study how the surface is reflecting light in a different wavelength, and you can divide asteroids into spectral types based on what fraction of light is reflected back in a given wavelength. So that's a very nice tool for identifying asteroids, what are they made of. So what about the future? So we are really looking into the future. As I mentioned, it's only 30% of any was found that NASA told us to discover. So there are hopes given into 2 devices. Number one is NeoCam, which is a suggested and prepared project that is still not fully funded, but I believe because the budget of the Planetary Defense is going up. So I think this thing will be funded. So basically it's upgraded NEOWISE telescope So it's a new telescope that should be launched hopefully in a few years. It's a much larger telescope. And it will have a different orbit from the WISE telescope that is rotating around the Earth. This one will be located in Lagrangian point similar to SOHO, so it will be between the Earth and the Sun. And we'll be looking in a different location of the sky as a typical telescope on the surface of the Earth. Because if this is Sun and this is Earth, your telescope is usually locating in the way that you are looking on the sky at night. Isn't that true? So you are only in this part of the surface of the Earth when you are looking at night. So this telescope, if it is launched ever, it will be looking into these angles. So we look into places where we never looked before, so we are going to discover those objects that are kind of hiding from us. So hopefully in a few years, this NeoCam will contribute to the discovery of more NEOs. And on the left, there is this large synoptic survey telescope being built in Chile. Should get its first light in 2020 and full operation in 2022. It's an 8-meter size telescope. It's not just a fiction, so this is the real photograph, I think, from this year, so it's almost built. And there is a little man drawn over here, so that's how large is this telescope. It's a survey telescope, so it will again scan entire sky. It can go down to 25th magnitude, so it's not for discovering an asteroid primarily, it's for other parts of the astronomy, but it will contribute with NEOs and other asteroids a lot as well. So this is again animation where NeoCam will look when it will launch. So totally different area of space as we looked before. So it should help us in finding more objects. So this is the prediction. So if we don't launch NeoCam and if we don't use LSST, this red curve shows you how good we are in discovering objects larger than 140 meters with current telescope that we have. So we are at 30% approximately right now. This is 30%. And if we go this way in 2035, it will be about 50%. So if we combine NeoCam and LSST, that will really bring us to 90%, but still in 10 years. So it's not really easy to find all of these objects that are around the Earth. So fingers crossed. So another part that is kind of interesting with the planetary defense is threat assessment, and this is a part that kind of is often mentioned in the media. So if you are watching media on internet, often there are news like there is an asteroid flying around the Earth. There is another asteroid flying around the Earth, and it's getting close and it's dangerous and stuff like that. But the thing is that these objects are flying around us have pretty good orbits at the time, so we know they're not going to hit us. But the trouble is, if you discover an asteroid and its orbit is very uncertain, it can have a non-zero impact probability with the Earth. So this is what happens. So if we discover an asteroid, has a very short orbit, a very short arc, so your area of uncertainty is very large. So the Earth can be inside of that region, and you kind of understand that maybe there is a slight chance of being hit with the Earth. So the impact probability is, very roughly speaking, just the size of the Earth or its area divided by the size of the entire region that is on the sky. But if you improve the orbit, that uncertainty starts to shrink. It's getting smaller and smaller and smaller, and eventually the entire area will go outside of the Earth. And at that moment, the uncertainty is zero. So basically, it will never hit the Earth. So this is the work that is mostly done at the JPL. So what about the threat assessment? So nowadays, people are doing studies. If objects hit the surface, what will happen? What kind of local catastrophes will be happening, like in terms of shock waves, thermal heat, earthquakes, the earth damaging, etc., etc. So this is quite an interesting part of the planetary defense as well. So there are also some mitigation strategies and missions planned, on the paper mostly, but we tried it on the Comet Temple with Deep Space Deep Impact mission. We already impacted something on the comet. So currently that's the best idea. If such a thing is discovered, we can try to use kinetic impactors to divert the asteroids on the impact curves with the Earth. So I can talk more about it if there is time at the end, but it's quite an interesting part. So once per 3 years there is this conference going on. It's called the Planetary Defense Conference that has an exercise as a part of it. So there's a group of people that meet for a week, and they kind of simulate if there is an asteroid discovered and it's going to hit the Earth. So this year the conference was the University of Maryland, College Park. So they simulated an object. So they really created something that is going to hit the Earth in like 10 years from now. And they kind of simulated the process of discovery, improving the orbit, and they've been computing where the uncertainty area will hit the Earth and where is the corridor on the surface. And as you're getting the orbit better and better, this uncertainty area kind of shrinks, and kind of, it was designed in a way it will really hit some part on the surface of this exercise. But what is kind of interesting, during the exercise, there was a space mission planned. Space mission that was going to go to the asteroid first, because we had like 10 or 15 years before an impact. So that mission will go to the asteroid, just stay with the asteroid and compute its orbit even more precisely to know where exactly it's going to go. But with the exercise, there was an uncertainty plan as well, so the mission failed. And these things happen in space. The mission could fail at the start, on the way, so that was kind of interesting. So within the plan, I think there was like 4 spacecraft sent to the asteroid as kinetic impactors. I think like 2 failed and 2 really arrived. And the asteroid was split into 2 parts. So basically 2 parts were are going to hit the Earth, but one was flying around the Earth. And the second one was, I think, impacting in this region as shown over here. It's Manhattan. So, but we had a lot of time, so there was in the exercise like FEMA was involved, there was a lot of time to evacuate and estimate the damage, etc., etc. So it's a pretty serious thing, so I think the Planetary Defense is getting into really good shape how to deal with threats like that, not only on the paper, but as I will mention in a moment from now, also in space. So maybe you heard about this mission, it's called DART, and it may start in 2021. So it's a mission to a binary asteroid. It's an asteroid Didymos. It means it's binary. There is a primary asteroid, there is a moon flying around that asteroid. It's a near-Earth object. And the goal of this mission, which is a joint mission between NASA and ESA, is to hit the moon. And the reason to hit the moon is to see how the orbit of the moon changes after the hit. So you will ask, like, why do you do that? Why do you do such a thing? So the reason is that we would like to study how the asteroid itself will react to the direct impact. And here is the reason. As I showed you the images, asteroids are kind of having not just a weird shape, we don't really know what is the internal structure, how the asteroid will react to the impact. Because it seems like the small asteroids kind of are not really solid. They have a lot of cracks inside, they are porous, so the porosity means there are void kind of spaces inside. It can really behave like a sponge, not really like a solid rock. So you can imagine if you take a baseball bat, if you hit the rock, or if you hit the ball, it flies away, right? But if you hit the sponge, it kind of behaves differently. And until we do that, we really don't know. So we don't want to try this mission on an asteroid that is almost going to hit the Earth, because what if you change the orbit, right? So you are flying to an asteroid that is still close to the Earth, but it's not going to hit us at all. And you are aiming even for the small moon. So this impact, this spacecraft is much smaller than the moon itself. It's going to change the orbit a little tiny bit. But you will have another spacecraft from Europe, Hera, that will be flying around. We'll just monitor how much the orbit of this moon changes with respect to the primary. And you can derive some properties like how is this behaving if you have an impact like that. So I'm looking forward to this mission. So it's not just about the DART, about the Hera. I think there are like at least 3 or 4 CubeSats associated with this mission. They will be flying with them to the release. So it's kind of a nice science endeavor in this planetary defense part. So there is currently a NASA mission at one near-Earth object, OSIRIS-REX. So maybe some of you are following. So these are images from the spacecraft, and the goal of this spacecraft is to bring samples from the asteroid to Earth in 2023. So currently it's rotating around the asteroid, the spacecraft itself. And the asteroid is pretty small. It's like not much larger than the Empire State Building in size. But it's in the near-Earth space. So there are some amazing pictures coming from the spacecraft already. So these are some images from the surface. So you could see from close that this doesn't really look like a typical science fiction asteroid, does it? Because that one looks like with craters on the surface, and the surface looks like it's a rock. But this looks kind of a pile of rubble, doesn't it? And you see kind of sharp pieces just lying around. And is this an asteroid, you would think? So it's just a loose bundle of rocks just holding together weakly with gravity. And there is some kind of larger rock on the right upper side. So this is how it looks from close. So we didn't know that a few years ago that asteroid could look like this. And look also the weird shape of it. So this is how it rotates. It kind of doesn't have a spherical shape. It kind of has a bulge on the equator over here. So it seems like it's kind of a loose rubble of rocks. With the rotation, those rocks kind of slip down to the region of the equator. So just imagine you will try to hit this with some rocket or with something. Well, you can imagine the kinetic energy wouldn't really even destroy it, probably. It will just dissipate inside, and you don't even see craters on the surface. What is this even? So you would think that must be some kind of thing that it's kind of rare, right? Isn't it? Well, another interesting thing that was discovered, it was only announced, I think, a month ago or 2 months ago, was that spacecraft is flying around the asteroid. There are particles flying from the surface of an asteroid by themselves. And we don't know yet what is causing this. But you know the particles are leaving the surface of the comets, right? Because comets are made of ice and dust, and the ice is sublimating when it gets closer to the sun. So it's just going out from the surface. This thing has no ice. It's basically dry, and those particles are as large as a few centimeters in size. They're just flying from the surface. Nobody knows why. So that's one of the most amazing things, I think, that were discovered around this asteroid. And you may ask, is this normal for this object? Is it, again, rare? So this is not the same asteroid, even though it looks the same. It's similar size. So this is asteroid Ryugu. And there is another spacecraft around it right now. It's the Japanese spacecraft Hayabusa 2. It looks almost the same. Look at that. Same shape, same features on the surface, only rocks, no impact craters. Maybe this thing kind of resembles a crater. But maybe we can change our thinking a little bit. Maybe this is a typical near-Earth object. It's not a piece of rock. It's kind of a piece of rubble. There is, again, some large boulder sitting on the pole over here as well. So it's kind of interesting nowadays to study how these things look like from close, and it has some consequences for planetary defense as well. So this Japanese spacecraft was pretty cool as well, because it has tiny satellites, or kind of almost CubeSats, that were released and landed on the surface. So these fantastic images are from these little tiny satellites that are kind of bouncing on the surface. So this is taken from the surface of an asteroid from up close. So this is, they call it rover Minerva. So this is from the rover Mascot that land on the surface again. And this is animation from the main spacecraft. You see the rover here, how it went from the spacecraft closer to the surface. So again, the surface from close is from after it landed. Look at that. It kind of doesn't seem very solid, does it?
Looks like it was put together by a government group.
Yeah. And now I'm going to show you a video that maybe some of you saw. So this is their attempt in getting samples from the surface. So they did that already. So you can see the shadow of the solar panels and how they got really close. So they were probably successful. They hit the surface. They even shoot the bullet before to release the gravel from the surface, and they catch it, the horn they have on the bottom. So quite amazing for a spacecraft. So again, they will bring the samples to Earth. So there is a lot of going on with asteroids nowadays, and some of the missions are really related to planetary defense. We like to understand how these asteroids work, how are they, what are they made of. So before I end my talk, and I'll be happy to take questions from you, there are some takeaway messages from my talk, like Earth impact risk is very low. So we should not be really afraid that something is going to hit us tomorrow, because that's such a very low probability. And I put this slide over here on the right, that you have much higher probability to being hit by the lightning strike than hit by an asteroid. So another thing is asteroid impacts happened in the past and will certainly happen, because it's just statistics. But this is one of the few, if not the only one, natural disaster we can avoid. We cannot really avoid earthquakes. or for tsunamis, you have very short warning times or no warning time in those disasters. But we can discover an asteroid is going to hit us in 50 or 100 years from now. That's a lot of time we can do something about it. And I believe we have the technology. So that's one of the advantages. So, and the cheapest thing to do about those is to discover them first. If you discover them, you know what's going to happen in 50 or 100 years from now. So, so close approaching asteroids you see on news are not dangerous because we know their orbits very well usually. Currently, all the discovered NEOs do not pose any threat to Earth, so in the next centuries. And we get to get ready for situations like this, so we had to discover asteroids first with the cheapest thing, compute the orbits, have the mitigation plan and the mission available if such a thing occurs in the future. And one good thing that I would like to mention is the asteroid discovery, orbits, close approaches, impact probability, and threats. All of these data are transparent, these data are publicly available, it's not hidden from public. It's even hard to kind of hide it from public because even amateur astronomers nowadays can discover and see asteroids on the sky. So it's really hard to hide anything. So these information are kind of public and we are happy to provide them to help observers. Not just the professionals, but Minor Planet Center also serves amateur astronomers as well. So thank you very much, and I hope you have some questions for me.
It sounds like we should be using this money to fix the flu.
We spend a lot more money on the flu.
So most of the money for currently from those $160 million, it was increased, it will go, I guess, to the space mission to NEOCAT. So it's not really funding more telescopes, that seems to be fixed, but this is kind of scraping money for the space mission. That wasn't really selected in the regular process, other missions were selected, so they are trying to fund this mission, I think it's good.
Has somebody actually tried to figure out the probability that there is something we haven't seen? What is, if anybody I don't know how you go about doing it, but is somebody trying to figure out that, what is it?
So that's the number in here, 1 to that part of million. So that's the overall probability, basically. Because you have to, you know the fraction that is discovered, you know the fraction that is not discovered as a function of size. So you kind of know what is hitting the Earth on average and how many people are on the surface. So you can kind of compute the probability, it's very low.
But it says you, so there's what, 8 billion people? Is that 1 out of 1? If we're going to hit 1 out of every million,
Yep.
6, that's a lot of people going to get killed.
That's in case of a large impact if it happens. Because that's integrated from the small ones to the large one. So it's much worse if the large one hits than the small one kind of injured. The Tunguska meteor injured like 1,500 people, not Tunguska, sorry, Chelyabinsk. There were injuries, and that thing even did not hit the surface.
If that had come in a different direction, slightly different direction, it would have made,
Yes.
it's about a megaton explosion. It could have taken out a major city.
I think like London, is it the same latitude?
Right. So it was something that could have been very much worse. The other thing to understand is that the telescopes are optimized differently. Atlas is specifically looking for small asteroids that, at the last moment, the things that we haven't been able to plan for a period of years. So it's optimized in a very different fashion than Pan-STARRS and Catalina and so on.
True.
And that's specifically because you can figure out, you can get enough warning to tell people to get out from underneath it. You can potentially evacuate a city that's about to be removed with a few days warning. So that's what Atlas is about. So it's specialized in that way. There should be, as I understand it, several more Atlas telescopes being built, but I don't know the exact details on that yet.
It would be a great military thing to be able to move into the city you'd like to have hit.
Really tough.
So when LSST hits the sky, how are you going to be able to data?
That's why we are increasing in staff. So 3 people hired this year, 2 people the previous year. So we are getting ready for that with the new pipeline, because that's the correct question. So we will receive like order of magnitude more data daily, basically, from LSST. So currently there are like 800,000 asteroids known with orbits, most of them in main belt. It can be 10 million in a few years from now. So it will be for us connecting the dots together, basically, because we are not receiving images, we are just receiving data, and it will be on our shoulders to compute the orbits and connect the dots together if they are correctly. So yeah, that's our job to deal with the data, and we only have like 2 years really, or 3 years before they fully start.
And let's just say you get data. Do you get some interesting things that you can find that aren't asteroids and stuff? As a part of your pipeline, do you find variable stars? Do you find other things?
So we just get the moving things, which are asteroids and comets. I didn't even touch the topic of comets, but obviously we also received observations of comets as well. So again, from LSST, we'll just get the position astrometry. So we just position, magnitude, and time. And we have to figure out whether it's known or unknown, and link it together, unlink, and so on.
So what's the minimum number of observations necessary to compute an orbit?
So sometimes basically it's just, 3, that's the correct answer, just 3. And of course the orbit is very uncertain, so what typically we do right now, even at this moment, what people are searching for NEOs, we typically send 4 observations that span 1 hour basically with a 15-minute difference. So from that you can sometimes tell that's an NEO for 100%. Because you can compute not a single orbit, but so-called bundle of orbits, so a range of possible orbits. And if all of them are in NEO space, that's an NEO, so it's really worth doing the follow-up. It kind of correlates with the motion. So NEOs are very fast on the sky because they are close. But not necessarily, because their orbits are often eccentric, so they can go all the way beyond Mars. And if you discover at the moment where they are far, they can really kind of move slowly. They can kind of resemble main belt objects. So, but the answer is like 3. That's the typical Gauss method, classical to compute an orbit. But it was meant for like 3 points, like basically weeks or basically month apart to get some basic Keplerian orbit. But with astrometry we have from these telescopes, after 2 or 3 days you have a decent orbit. So with much shorter arcs, but very dense coverage from many telescopes. That's what we do mostly for NEOs.
You briefly mentioned comets. Now, comets are also a hazard, but they're much more difficult to deal with because a new comet can come from virtually any direction at very high velocity.
True.
You have very little warning, perhaps, and mitigating it would be very, very hard. You'd have to match velocities with the comet, which would be possibly impossible.
That's true, but someone computed at least 1 or 2 papers, I remember. That probability is like 1 or 2 order of magnitudes lower than asteroids. It's just about the numbers. Of course, you are right, because the velocity that is between the asteroid and the Earth, it's much, much lower than the comet. For asteroids, typical impact velocity is like 10, 20 kilometers per second. Comets could go like 60, 70. And with the velocity and the impact energy, kinetic energy, scales as velocity times velocity. So not really mass, but the velocity itself is the trouble.
So Peter, you mentioned the Planetary Defense exercise, and I saw in passing IAWN. A few years ago, I was involved with a sort of simulation. If you discover for real that there is an asteroid that's going to hit, let's say, Syria. And I picked that intentionally because this was a UN-sponsored exercise, and the notion is, who would you call in Syria to let them know that the asteroid was going to hit? Would they believe you? Because not every country, has a lot of faith in the United States. Does the defense exercise explore these sort of geopolitical questions?
Oh, it does. I can mention this is a lot of fun with the exercise itself. So when the exercise starts, it's not just about astronomers. There are like, I think, 8 different groups that were created, and one were even politicians, one were press, one was the United Nations, so one was even public. So it was interesting interaction, and even with the asteroid mitigation. So one of the plans was just to send a nuclear kind of device to blow up near the asteroid, not really on the surface to destroy it, but just to create a thermal emission on the surface. But it wasn't allowed at the end because in the simulation, the international community did not allow to send anything nuclear weapon to space. It's even banned, I think, by nuclear treaty, outer space treaty to send anything to space, even for saving us. So in simulation, really, there are these political arguments as well. That's number one. Number two, you just mentioned randomly Syria, but just imagine that this path is going through, it can go anywhere. It goes through Russia and China, and somebody is sending kinetic impactor. And you can change the orbit in a way, it will just move along the line. So it won't move the line this way or this way. So all you do if you change the impact, it just moves along the line. You can just land in China instead of the ocean. And that's kind of a politically question that. So yes, you are right. So this was also kind of solved on the political level. And I'm afraid, so if scientists are doing these experiments in their thoughts, it's always much easier than in real life. Because if you start to bring like politics in different countries, I think in the real life it's much more difficult.
You can watch these conferences. They're online on YouTube. I've watched.
Oh yes, yeah. The last one is
not this last one, but the one before, and it's interesting to see that they do have representatives from serious parts of the U.S. government, like FEMA and the like. So they try to project some reality, but you're right. It's going to be when this thing sort of happens, from Chelyabinsk or worse, you may have some interesting geopolitical problems.
That's true, really. I mean, it will be interesting, but fortunately, if such a thing is found, we have like 10, 20, or 30 years before, and who knows?
Except for the little ones like Chelyabinsk, which we could get, which we'll be lucky to have a week's warning.
Oh yes.
Speaking of Chelyabinsk, has anybody gone back to look and see if we'd had the second advanced stars telescope sooner, or LSST sooner? Would we have seen it?
Not this one. It came from the day side.
Came from the direction of the sun.
So that's the thing. So many of those, like Chelyabinsk type, could be discovered with LSST when it's kind of far away with that orbit. But many times those orbits are kind of made in a way, and there's a type of orbit called Atira that is entirely inside of the Earth orbit that we don't see at all at this point. So half of the sky is basically the night, half is day. So it's still that part of the problem.
The best that Atlas will ever do is about 60% of the sky. That's because you can't look too close to the sun.
Just at night.
Just at night, and even with multiple sites in various parts of the world as planned, they'll get 60% at best. So at some point, you got to put you have to put the satellite up. On the other hand, the ground telescopes are way cheaper. So
true.
Yeah.
Yes. Yeah. So there are even some challenges with NEOCAM. As I mentioned, the NEOVISE is orbiting around the Earth. It's basically on the polar orbit near Terminator. So that has a luxury, like the NEOCAM is looking like these directions. Kind of not really directly into the opposition, they are kind of looking closer to the sun, but not as close as the NEOCAM could. I was mentioning NEOVISE. But the problem with NEOCAM will be in L1, in Lagrangian point, so that's pretty far from Earth, so they will need to kind of send images. So you have the bandwidth problem and a lot of data transfer, so. But true, if you have something like that, you suddenly see a lot of stuff that is much closer, even the Chelyabinsk style thing. Even though it's like 20 meters, this should look kind of much deeper in terms of limiting magnitude and infrared. These are NEOs that are relatively hot on the surface, so they're much brighter.
One of the counterintuitive things for the small asteroids that, like Chelyabinsk or whatnot, is I asked John Connery about this and whether you would expect them to be coming in roughly on the plane of the ecliptic. But apparently, by the time they're near Earth, their orbits have been pretty well messed up, and so they come in relatively isotropic distribution, which you wouldn't initially expect. I was quite surprised when he showed this to me. He actually had some simulations which showed that kind of thing.
So actually wrote a paper in 2007 on the topic of observing impacting asteroids with fast stars, so the distribution in the sky. So interestingly, they have pretty low impact velocity from asteroids, those impactors, statistically. So that's the good thing that people in Russia have dash cams on every single car of yours.
Is there a formal definition of what is a NEO? I mean, is it a certain range of astronomical units within near its orbit?
So the definition is relatively simple. It's the periodic distance smaller than 1.3 AU. That's it. So you can imagine in that category you have objects never really get close to the Earth. Those are ATMoBs. Those orbits are entirely outside of the orbit of the Earth. But even if you have asteroids that sometimes cross the orbit of the Earth, they can be pretty far away, in 3D space, those orbits. So definition is pretty simple for any of those. Q is less than 1.3 AU.
You mentioned the use of radio telescopes like Goldstone and Arecibo to characterize these. Is there any indication that the 500-meter aperture telescope coming online in China soon will be used for this kind of work? And could you comment more on what sort of international collaboration there is between NASA, ESA, ISRO, JAXA, and so forth?
So about the Chinese telescope, I don't think they have a capability of doing Doppler. So I think they are just receiver, not transceiver. That's what I heard. So they don't. It's not radar, just receiver. About the international collaboration, that was I think mentioned in my image, but didn't this way. So basically, with collaboration, it's this part on the bottom. So basically, there are some working groups, even the United Nations, and there is one group that is called YAON, International Asteroid Warning Network, where some institutes are involved and kind of collaborate things. If there is an object that has kind of high impact probability, they will kind of contact these observatories that are in the network that can help almost immediately. So ESA has their own group. It's I think called SSO. It's Space Station Awareness, part of that program. So they also have some telescopes. They are not contributing significantly into discovery, but they are contributing with computing also impact probability independently, which is also quite important. There are like 3 groups in the world that are computing orbits independently from our data in impact probability. It's better being safe than sorry, because someone computes it, we compute it by a wrong way. So the international collaboration, I think it's getting better. But I can mention that most of it is still done in the United States, like 90%.
Both financially and
even the telescope, even organizations. But we are trying to attract also other nations into collaboration, and it seems to be working. I think Europe is putting a lot of money into it, other countries as well. So hopefully more will be joining, not just with the telescopes, but also we need space missions as well.
Last question, maybe? You mentioned that the asteroids appear gravelly in nature. How is it that they don't just break apart into a whole bunch of pieces once they enter Earth's atmosphere?
So that's a good question, and it actually, maybe they do. So maybe that's the case of Tunguska, because Tunguska was probably like 40 or 50 meters across. So it caused a giant explosion. Maybe you saw some graphs, what kind of surface area was devastated. It was like, I don't know, 1,000 square miles. But it was kind of amazing that it exploded like 30 or 40 kilometers above ground, pretty high. It's kind of, in theory, it was probably a piece of a comet, basically, made of basically just ices and dust. It just didn't withstand the stress and the temperature of the pressure, just exploded. Or it could be something like this. So actually this thing is much weaker and never reaches the surface. Like totally different case is the Barringer crater. That was an ironical object that was probably smaller, like 20, 30, 40 meters, they say, 40 meters. So it really hit the surface basically unaltered because it's iron. But if something like this is weak, hits, well, the problem is even though it kind of looks weak, it's kind of pretty fast. So it takes a fraction, basically a few seconds before it hits the surface. So it's not really decelerated very efficiently. So even though it's kind of loose, the energy will basically be in the impacts of the mass that is coming. So I think it's not such an advantage for us if things like this hits. It will still hit as a kind of single body.
Okay.
If it hits us straight away. If it is like really approaching slowly around the Earth, it could actually stretch or even lose some mass, but like direct hit won't really matter a lot.
There are a lot of different kinds of asteroids, and they have very different physical properties. So if you have a nickel iron thing, it's really like it can be very much a solid thing that looks like a big piece of iron, right? But you have carbonaceous chondrite or whatever, some of the other forms, they're much more fragile materials.
So these are actually carbonaceous chondrites,
Right. So
these things.
so it's not surprising that we see a number of different kinds of asteroids.
I want to take an opportunity to thank you again and all the great questions. All right. Lights. The lights. No one's walls. So again, I want to thank everyone for attending. Just so you know, the Patriots are winning 21-14. Very crazy game, if you're into that stuff. I want to thank Maria for providing refreshments after the meeting tonight. And just so that people are aware, next month I have a speaker lined up. It's Dr. J.J. Hermes from Boston University. And he's going to be talking about the plunging pirouette of two low-mass stars. So it should be really interesting talk. So a little different than what we saw tonight. But thank you very much for attending, and thanks again.